What do we need this for?
I guess I don't know. You don't need it. Basically, what you set up the camera.
Yeah, I thought we didn't need the integrity at all. Okay, so should I turn it off? Is that okay?
Integrity on to right on your.
Oh, you do?
Yeah, you can use that. The small.
Okay. Yeah. Well, I've just been using the journal.
Oh, okay.
I've just been using this. Okay. All right. I think we're ready to start this time.
All right.
On time today. It's all good. Question? Can we lower down a little bit, bring it in? We're actually starting on time this time, so we have to listen. Okay, question. You derive the modified measure of performance right here. So then you want to. So yeah, you want to do something similar to these figures here, and we're going to actually go over these figures today. But you want to come up with something in here is instead of the initial mass ratio, some other figure metric for that split, and then in that case you're going to use this one that you've derived here. Yeah, yeah. Yeah, so you just need to figure out, so this one's versus energy split. You obviously don't have energy split as part of this equation. So, use the equation as a section 3-4, which is what we've been driving through here, to use this performance metric to come up with sort of a representative plot. So, yeah, it's going to be something similar. Also, relative to the examples, the question I had before was the 778.2 conversion factor. It's actually really easy. It's 1 BTU is 778.2 foot-pounds. So if you had gone and just reversed the engineered the units, you would have come up with the same thing, but that's where that comes from. 1 BTU is 778.2 foot-pounds. Yeah, that's why everything should be SI. It makes life easier. Okay, so what we had planned for today was to finish off Chapter 3 and then get into our seminar. And so depending on where we get, I'm hoping we can get this seminar started. I don't honestly think we're going to get it finished because it's a good half an hour, maybe a little more. So we'll go as far as we can, get the notes done for Chapter 3 so you're set for the homework, and we'll start the seminar and finish it off next time. And then what we'll try to do next time is then catch up a little bit more and try to get ourselves back over next week. But where we're starting next week, let's go to the very end here, is ramjet engines. And so for ramjet engines, I have some handouts I'm going to give you. Probably the easiest one is from Hill and Peterson. It's a whole chapter. You'll see the section in there. It's probably 5.2 or whatever part it is. It's not that much, but that's kind of where we'll start. I gave you the whole chapter, so if you're looking for the context, it's all there. Where we start here. So some of just the background part. So 5.3 is where we'll get into, and then we'll get into some other details from there, as well as a chapter from Kerbrock, which is twisted, rotate. And this is, I think, chapter 2 in this book. So you'll see down here the the ramjet. And the reason I'm doing both is because what I'm going to be showing you as we get into next week and the week after is kind of amalgamation of these two plus some other stuff. So there's not really one good reference, and this book is not a good reference either to start the fundamentals. We're going to kind of build everything from the same building block and extrapolate out. So I like to at least touch on the basics, even though a lot of you have had it before, and then move quickly through them. Also, there'll be another equation sheet. Some of the one you have looks like this one. It's got all the important equations for the ramjet, scramjet, ideal ramjet, turbojet, afterburning turbojet. So kind of everything we're going to spend the next little bit of time on. Here's the equations, and so you kind of have a heads up on what's going on. So let's close that. As well as, I'll just kind of give you the details now. For the seminar, there's 3 journal papers, as I was talking about. This is a group I was working with when I was at the University of Maryland. It's particularly the student, Adam Dissel, who I was mentoring. And so a lot of this work came off a series of 3 journal papers he did for his master's degree, which, if you're doing a master's degree, is a phenomenal accomplishment in itself to get 3 journal papers out of it. But weight growth study for reusable launch vehicle systems is one. And these are just kind of extra reading if you're really interested. Investigation of 2-stage to orbit air-breathing launch vehicle configurations. And the third one here is comparison of horizontal and vertical launch. So the seminar is kind of amalgamation of all these 3 things to kind of give you the flavor that the book doesn't give you of what's really happening when you put these systems together in a more complex way. And that being said, if you kind of follow where NASA is going right now with the NASA administrator and even the new chief technologist, is you'll see actually this name. Oh, I lost my chart. Let's go at least over here. You'll see this name showing up on some of their new charts when they're talking about launch vehicles. Actually, is Astrox, which is it's a very small company, but they're the ones who developed the software that was used in all these studies, and it does a really good job of just kind of comparing things apples to apples. Yeah, see, now we've crashed this computer. So if you see this little symbol on some of the recent NASA charts, and I saw some as recent as a few weeks ago, they are a very respected company in doing launch vehicle designs and trade-offs. They're essentially the company, along with Pyrodyne and Fred Bailey, if those names mean anything to you in the scramjet world, who helped start the inward turning inlet, I would say, revolution, which is kind of taking over the scramjet community right now. So if you see work by Astrox, have a look at it. It's very good work. But we're going to cover this. Hopefully we get started on it today. Okay, but now we have to take some notes first, so we can do our homework. So we finished off the air breathing. Access to space is where we left off last time, and so now we're going to do the rocket and then the multi-stage vehicles, and then get into the seminar. So lecture 6. Let's just call it Rocket to Leo. Okay, so this derivation is going to be really similar to what we did for the air breathing. Of course, when we get to the right point, we're just going to put in some rocket terms instead of air breathing terms. So there's not really going to be a lot of details here that are important. But we'll step through really quick so your notes are complete. See if I can get an A in here. Axial force, which goes to our mass term, our velocity term, thrust drag, weight sine theta, change in altitude, where our change in altitude, which is the same as we did before, dr dt is v sine theta. So we obviously have to do a little bit of rearranging to get this term into our force equation in order to have it make some sense. I really applaud you for having to read this writing because it's really squiggly. For it to make some sense, we just multiply everything by v so we can get our force equation to match our change in altitude term, and then plug it all in. So we get mv dv dt. We're just going to multiply both left and right sides by v. Thrust minus drag times v minus mgv sine theta. Anybody know what thrust minus drag times v is? Yeah, it's essentially it's your power term. So it's your net power, it's your power available, If your drag equals thrust, you have no power available. Rearrange again, pull the V in. DDT. So hopefully in another lecture or two we'll get caught up and I can slow down and write legibly. Okay, so we substitute our dRdt, which is our R is our altitude term, our radius term. Just make a note in there so everything makes some sense. So this is kind of where we were for the most part for our air breathing system, and then we started to look at putting an air breathing term there for the thrust. In this case here we're just going to use the rocket term where we had ISP equals what? Come on. What's that? Oh yeah. Well, in this case, ours is F. Yeah, over yeah, m dot FG is our weight flow rate of fuel. So we have to do the same conversion we did before, where our thrust is our uninstalled thrust and a loss factor, so everything kind of looks the same. We have our drag factor. Our velocity for the rocket is just inverting this guy is G naught ISP. So we're going to put this all together to get our thrust term, our installed thrust term, G ISP, our mass flow rate change minus our drag. So we're going to take this guy here. If I can finish my box. We take this guy here and plug it into our force equation that we have. So, you know, any of these systems, hopefully you see, like anything else in engineering, really, it's boiling down to something simple, putting some assumption to it, and then working it out. So there's nothing that we've done here that's complex. It's just kind of fundamental equations, going through some nuances with propulsion. Not even really too concerned with what we're really talking about for propulsion. It's all black box at this point, and then moving forward. So I like to think of this sort of level of detail for any of you who are, you know, kind of PhD students or going through PhD exams. This is kind of fundamentals. You know, if you can kind of wrestle through fundamental equations and apply them to a new problem, that's kind of what a good engineering is, right? So nothing tricky here. Sometimes you have to understand the tricks that were applied, but there's nothing really tricky here. Okay, so I think now I'm going to skip through some of the rearranging terms there where everything's plugged together and just get to the answer. And again, there's nothing confusing that went on to get here. It's the same as we've done 3 other times already. Our velocity term, our potential energy term, and in the denominator now we have rocket terms. So in order to integrate this, we have to do a big assumption again. What's that? Denominator is about constant, yeah. Denominator assumed about constant. Make our lives easy so we can do our integration. The potential energy term we're going to assume is going to go approximately to 0 relative to kinetic energy term. So relatively it's small, we're going to get rid of it. You know, as we saw before for low Earth orbit, it was about a 20-to-1 ratio, so it's reasonably good assumption just to make ourselves make life easy. We're also going to assume our initial velocity is much less than our final velocity. So when we do this, we can just get down to our final velocity term. So the result, so all these assumptions are essentially the same as we did before. Mass final over mass initial is the exponential value of minus V final. Oops. Make sure I get my terms right. V final divided by our rocket terms. for Leo. Okay, so we get an equation that looks very similar to what we had before, but in this case we have a couple of fundamental differences. We don't have efficiency. Instead, we have a specific impulse. And in this case, we actually do have a velocity term, whereas for the air-breathing system, we did not have a velocity term that showed up there. We reduced it all to energies. In this case, we have a final velocity. And if you're wondering where the squared went, you see the v in the denominator. You just work it through and then cancel it out and get rid of it. The system then makes something a little bit more sense. So in this case, we have this final assumption. Oh, so now same as before, we need to get that velocity in terms of our energies, and we did this one before, so I'm not really going to repeat it, other than just give you the details where we have our other force term, mg cos theta minus L. So for this case, lift is going to 0. We're going to have this is going to 1, small angle, v squared equals gr. Do my math right, get rid of the m's, yeah, we're good. Which equals g naught, r naught over r. So if we're talking for Leo, r naught equals r, close enough, which goes to v equals square root of g naught r naught, which gives us about 7,900 meters per second as we had before. So same sort of little derivation that we had before, just get a velocity. So we have a velocity term. We could just leave it as square root g naught r naught if you just wanted to be symbolic and be nice and pretty. Oops. Way too many notes here. So skip ahead to our mass fraction is now 1 minus mass final over mass initial, which we just derived the mass final over mass initial is 1 minus the exponential of g naught r naught over g naught ISP Okay, so let's just write this guy over here so we can box. So our fuel mass fraction in this case is another somewhat messy looking equation, but we have a thrust to drag term including our installation loss. We have an energy term, which is just our orbital, low Earth orbit energy, and we have a specific impulse for our engine. So it's not really a lot of details to worry about here. For rockets specifically, thrust to drag is a lot easier to work out than for an air-breathing system, which is a lot more complex. So in this case, this equation, you actually can boil it down to something you can do sensitivity analysis on much easier because it's kind of more fundamental than the air-breathing. But if we look at kind of the nuance of what this looks like now, of course, from the book, what's the first thing you see when you look at this plot that is a little awkward? Crazy high specific impulse. Yeah. Yeah, so this is, once we get past what number is bad? Yeah, right around here, say 450. So most of this chart is useless. But what it's really telling you is, for a rocket to get to low Earth orbit, single stage, you need incredibly high fuel mass fraction. You need fuel mass fractions in the 80+%. In reality, a lot of rockets are in the 90 percentile. It's very little payload, very little structure, very little payload with a little bit of added structure in the actual direction to get a lot of fuel and engine hardware into orbit. So, yeah, it's mostly just one big fuel tank, as you would guess. So what you see here, though, is if we can imagine rockets that had specific impulses that were in the non-real range, you could get something which made a little bit more sense. But if you kind of think backwards, actually I don't even have the chart here, to what we looked at last week, or last class with the air breather. What number are we on here? We are talking the similar fuel mass fractions. Ooh, where did we go here? For that orbital radius, you know, in the 40 to 80 percentile. So, you know, the composition of the vehicle is very different, and of course we also said that you're not going to get a single stage air breathing complete orbit. It's going to have a rocket in there somewhere. So, you know, these are still hard to compare. They're not, you know, exactly apples to apples where we can lay one over another. But what you do see is when you design a rocket, you have to design a very efficient structure. You know, that's kind of what you're going to get at here. When you design an air breather, you have to design a very efficient engine. Rockets are just kind of good. You know, you mix some fuels together and you're going to get it generally to work as soon as your turbo machinery is right. Okay, so if we look at this system here, let's go back and write a quick note just as a comparison. Escape. There we go. So for modern rockets, ISP is less than about 450 is a good guess, which goes to greater than about, we'll say 80%. It's a little bit higher, but that's a reasonable number. So comparison, we'll have a little table here, takeoff weight, fraction, we'll have an aircraft, and we'll have a historical system here. Can't write. Saturn V. And this is multi-stage, so it's kind of cheating, but that's okay. And these are just kind of representative values, so don't lay everything exactly on these numbers, but payload, empty mass, fuel mass, and oxidizer. Let's just call it oxygen. Aircraft, 15% payload. Guess for a rocket? Yeah, it's 3, 4, tiny. Empty mass fraction? Guess for the rocket? I'll put 7. Yeah, fuel is going to be the big one here. 30%. Yeah, that's okay. There's no stupid answers. Okay, and of course oxygen here. So this is not necessarily a good comparison because this aircraft is not going to space, but it's kind of always this one thing that we say when we're pushing why air breathers have an important role to play is when the technology actually gets there and you can get rid of oxygen, 65%. You know, that's a huge weight savings. If you get rid of that oxygen and only need maybe a little bit for the final push into space or even the final push or to push for takeoff, whatever you happen to use it for anywhere you need high thrust, that's kind of the benefit. Now, of course, the technology is not there to do this with air breathing engines yet, but you know, as we keep mentioning, we're getting inching closer and closer every day after 50 years of development. Okay, so that's the end of that one. And there's some good details in the book, and I'm not going to spend time on it. Hey, my chart disappeared. I'm really not going to spend time on it now. Talk about empty mass fraction, just kind of what you need to think about. And so it doesn't really matter if we jump forward. But if you think of this chart, historical empty mass fraction, this is kind of where if you start preliminary aircraft design, this is where you always look. You have some sort of frame of reference. You say, I know aircraft in my approximate class, approximate size, approximate mission, whatever. You pull up a chart like this, and there's a curve fit through some historical data. And, of course, there's a lot of variance. It doesn't always fall on the curve. But what you see here is an empty mass fraction as a function of initial mass. So you plug this into some computer model, and you get some sort of rubber scaling for what your empty mass fraction is going to be for what you think your initial mass may be, or vice versa. You know, if you're trying to use it as a requirement, you have a very efficient structure to give you an empty mass fraction, and you figure out what initial mass you have. It doesn't really matter, but what you see here is a lot of historical aircraft, and they kind of fall fairly nicely around this line. And you can kind of have some warm, fuzzy feeling in your stomach that what you're doing makes some sense because it follows this historical trend. And I would say the number one fundamental problem with this sort of analysis for hypersonics is what? There's no historical trends. Everything is extrapolation from what you're guessing your performance is, so you can sell a program to somebody, get a lot of money to develop something, fall short of that line, and hope you get some more money to do it and finish it up later. So, yeah, extrapolating from a big unknown to a further unknown is a hard thing to do. And so that's kind of why the papers that I showed you and the seminar we're going to talk hopefully today kind of deals with that, of how to address some of those issues of when you're dealing with the unknown, and you see how programs are sold. For instance, the NASP, National Aerospace Plane Single Stage to Orbit, was originally sold to Congress at 100,000 pound takeoff weight. You know, when it finally blew up, and blew up is the wrong term, when the program finally shut down, it was orders of magnitude heavier than that. You know, it's because of those unknowns. Empty mass drives everything we talked about. Empty mass driving costs, operational costs, procurement costs, maintenance, everything else that you need to worry about when you're thinking of these systems, but you're kind of dealing with a giant unknown. So the seminar we're going to talk about kind of talks about this from the aspect of rocket versus air breather versus single stage and multi-stage, and how to think through it. And the way that it's done in that case is called a growth factor. And really what it is a sensitivity analysis of all the input parameters and how it drives output, and kind of where you're on a risky slope. And I think I mentioned on the first or second lecture, you know, there's kind of I wouldn't even necessarily call it a new push, but I would say it's a really strong push in aerospace engineering now, taking a big lead from the nuclear community to take that, you know, away from what's called a sensitivity analysis, which is kind of a poor man's analysis of let's just vary one parameter at a time, to an uncertainty analysis, which is how you take all that information and understand what you're really doing, what the risks are from the you know, the kind of the pure stance, not just looking at you know, a derivative of one variable with respect to whatever else you're looking at. But regardless, no, this is kind of an interesting driver, because preliminary design, this is what we always do for aircraft. For spacecraft, you know, we're kind of on a giant unknown. And the other problem is you know, especially if you think about spacecraft, you know, even the crew exploration vehicle in the Orion, you know, what drives a lot of those decisions is what? Well, politics is huge, but the politics are driven also by what have we flown in the past? What do we have a lot of confidence in? We know this material because we flew it 40 years ago, so let's use it. And that's kind of, you know, progress is really slow to be introduced. And so something like air breathing access to space, you know, we're not even there with technology yet, but let alone implementation, is going to take a lot longer. So maybe by then we'll have a curve like this. I don't know. Rockets is actually, you know what, that's what my previous chart that was blank was. I have a really great curve to go in there, so I'll bring it next time. But you'll find the empty mass fraction for rockets, you have a similar curve, but it's all in the 90th percentile, kind of right around there, and there's a lot of rockets that fall in there. So it's, you do have a lot of good historical data for rockets. It's a empty mass fraction is, oh sorry, no, I'm thinking of the fuel mass fraction. Empty mass fraction is more in the single-digit percentiles. But there's a lot of historical data for rockets that fits in there. Okay, so we're going to invert this a little bit more now. Oh yeah, so we're not going there yet. And look at the initial mass ratio. All right, anybody read the book? Remember what initial mass ratio is? What's that? Not quite. You're getting close, though. There's masses involved. Come on, somebody want to guess? See, you're getting way advanced now. But no, you're getting the right thing. But what is the fundamental definition of it? What's that? Yeah. It's the 1 over pi p, which is the initial mass over the payload mass. So it's what is the fraction of multiplier of payload that our initial mass is to get to what our system's looking at. So I don't think actually we define these. They're all kind of defined the same, and I know you've read the book, so it's all easy. But empty mass is our empty mass ratio is mass empty over mass initial. The fuel mass fraction is the fuel mass over mass initial. Payload mass fraction here is the payload mass over the mass initial. Everything's just always divided by mass initial. So if you got to that problem, you've already figured this part out, so that's easy. So we substitute this in, we have our, as we just mentioned, this guy here, and what it's going to boil down to is 1 minus pi e minus pi f. And how do we get that? Where did that substitution come from? Yeah, it's just by definition. You know, pi e plus pi f plus pi p equals 1. That's all it is. It's all the masses have to add up to initial mass. So just substituting that in to get this gamma equal to this guy. So there's no trickery there. So what we really want to do is have small gamma, right? For a given mass of payload, we want our initial mass to be as small as possible. That's kind of what our driving parameter is. So we would like gamma, that looks like a gamma, to be as small as possible. For a given payload. So all it is giving us another metric to kind of measure things against. And like we've said before, there's never one metric that tells everything, and this one is the same. It's not going to be the one that the holy grail of gives you all the information in one little nice package, but it's another nice one to compare against. So we do know gamma will increase as our empty mass and our fuel mass increase. So that's kind of our goal, is reduce the fuel, reduce the empty mass. So there's nothing kind of tricky here. It's just exactly what we're interested in looking at. But for what we're kind of thinking of for the empty mass, though, we'll just rewrite it. 1 minus the fuel mass minus 1 over gamma. So just rearranging to get gamma as part of our new metric for our empty mass fraction. We're going to use this guy for some of our new metrics that we derive. And in the interest of time, I'm not going to go through the books or through the examples in the book. There's, I think, 3 or 4 little examples, 5 little examples, 3.7 to 3.11. There's nothing complex because they're all plug and chug equations, so it's kind of silly. But you can look there and get some sort of relevant numbers for at least what they're putting in there. Not that they always have a good meaning. But so if we take this guy now and revert back to our equations and plug this guy in, I mean, essentially we just take the equations we've already derived. Oops, that's not what I'm trying to do. Let's do that. And rewrite them. Our overall efficiency now we can rewrite in terms of a gamma function. And I don't actually have the old chart, so you can't really compare the two. But so if we're looking at to have gamma be as small as possible, you know, this curve here with 20 is not really what we want. The curve here with 10 is not so bad. The curve here with 5 is really desirable. The overall efficiency here, what you're seeing, oh, sorry, I should caveat this. This is a hydrogen cruise aircraft, air-breathing aircraft. So it's air-breathing. The efficiencies for empty mass fractions here, we're talking somewhere in the 40 to 60% is not a bad empty mass fraction for that aircraft example we saw. Now, of course, that's not a same sort of aircraft, but it's a good representative value. So somewhere 40 to 60%. We're looking at efficiencies anywhere from whatever here, 25 up to 45, 50. So 50% efficiency for an air-breathing engine for these sort of applications is pretty high. So we're already talking that our mass ratio is going to have to increase, our initial mass ratio, something maybe the order of 10, which is going to drop those efficiencies down. So we can have everything's going to start to scale. It means we have a bigger structure to do the same sort of amount of payload. And for a cruiser, payload is, you can guess what payload means when you're talking about a hypersonic cruiser. It's probably a one-shot mission, terminal. But in order to get something desirable, what you're seeing here is the change between 10 and 20 doesn't look that bad. Well, all we have to do is increase our initial mass, and we're buying a little bit of change in efficiency, which is good. You think of how it relates back to everything else we talked about, changing an initial mass is not good. You know, that's going to make the vehicle scale up. It's going to balloon. So this is hard to kind of see that difference between a 10 and a 20, but you know, essentially what we've done is double the initial mass. You know, so a very small payoff in terms of what we can have as an engine requirement for a very large change in mass. So in the end, we really just need better engines. I think the next one here, this is hydrogen accelerator. Same sort of thing, but now what you see is the efficiencies are very, very high. Any sort of empty mass fraction above 0.3, and all of a sudden, hydrogen single stage to orbit is really just kind of, you know, we need to have very, very light structures. You know, starting to approach rocket sort of structures. Not quite, but very, very small, 30% and lower. The hydrogen, oh, we're not there yet. Don't look. You know, I'm missing a chart. I didn't have the hydrocarbon guy in there. What you see, though, is for the hydrocarbon, I don't know what happened to my hydrocarbon picture. Did we skip over it? Hydrogen. Oh, there it was. We did skip over it. For the hydrocarbon case, it's also equally bad. We need very efficient air-breathing engines. So hydrogen is the only thing that's showing some sort of promise here in getting us down to a lower initial mass ratio. Everything else is showing us I need a very efficient structure, low empty mass fraction, and I need to have very efficient engines even to make this somewhat feasible. And so that's kind of where you see, if you think back to the NASP days of the 90s, trying to sell single-stage to orbit air-breathing engine is built on curves like this, and you're exactly in the wrong spot. You know, we don't have technology to push those engines to those efficiencies, and they especially didn't back then when they hadn't moved anything out of ground test. So, you know, it's kind of interesting when you look back at some sort of historical, and even if you think back to this book was written in the middle of the NASP era, 94. You know, this sort of just basic logic tells you that it's kind of a long shot at best. So, but don't worry, I think we've learned our lesson on that one, hopefully. But so hydrogen is promising. Hydrocarbon is not looking so great, and the access to space, of course, is looking problematic. So, what do we see here? Oh, so let's make a note on that one, I guess. For the overall efficiency required, based on those charts, what we're really seeing is this is going to drop dramatically. For change in fuel, which is obviously the curve showed that very clearly, but it's just driven by the change in fuel. So hydrogen is a clear winner, and of course lowering our empty mass fraction, which really just means, you know, more room for fuel. So kind of a good guideline, and you know, this is kind of a subjective because it's based on a lot of made-up numbers, but the kind of good guideline is, and I'll write it down, then you can laugh, and then we'll talk. How about that? For profitable commercial operations. You know, I can start laughing. Wow, I can't write. Operation gamma should be less than 10. So it's kind of a good stretch. It's kind of where the, if we see some of these FedEx things ever coming to life, this is kind of where you need to push it down to. And if you kind of go through the same analysis and put Concord on here, what you see is, you know, Concord never really had a chance. You know, some of these things you can kind of go back to basic metrics, do a financial extrapolation forward based on number of flights, you know, distance, you know, cost, et cetera, and realize that you have to have a very high cost. And so, you know, that's kind of a good driver looking at this initial mass ratio. So if we look at something that has a lot of fuel, which is minimum empty mass fraction for a KC 135, so fuel tank is 0.35. So that kind of gives you the bottom range of those curves. So if we look at where this drives, and this is just taking numbers off the curves again, a minimum efficiency for hydrocarbon, if we're way down there, is about 45%, and for hydrogen, as we mentioned, is about 20%. So hydrogen is clearly a winner, both in terms of what it's doing. It's lowering the weight, it's giving more energy, and it's giving you kind of some more favorable numbers in terms of required efficiency. So hydrogen, is clearly, as you see, if you kind of follow literature, hydrogen is always the fuel of choice when you're talking access to space for air breathers. And this is kind of what I call is the misnomer that we'll talk about in the seminar as well, is maybe why that's a little bit misleading, because it's only one way to look at it. But anyway, if you look at kind of the drivers here, what you see is we need to do better for efficiencies, especially if we want hydrocarbon, but hydrogen is a clear advantage. Oh, here's my other number, Concord. Is around 45. Okay, so that's enough of that. We're running out of time. It looks like we may not even get to the seminar, but that's okay. Let's get through the notes, and we'll hit the seminar first thing next class. So what we now want to do now is kind of where we were leading to, is how do we put this together in a way to make our lives better, which is multi-stage vehicles. Okay, so why is multi-stage good? Yeah, you get rid of mass, and anytime you can drop off mass, it's going to change how your equations all look. And less mass to drag means better thrust and better acceleration, and you're getting all of a sudden your fuel drops and everything's looking better. So drop unneeded mass. That doesn't look right. Early in flight. So essentially we can pitch stuff overboard. So obviously this is not built on an environmentalist agenda, because we're just dumping all kinds of harsh stuff over into the ocean, but that's okay. So it reduces our total energy. Or fuel mass required. And leaves more room for empty mass or payload. Okay, and the last thing is staging increases our gamma. So if we look now to the basic parts that you're looking for in your equations, we'll just do some simple bookkeeping here. Single stage and two stage. And you can kind of extrapolate this to as many stages as you find interesting, and in many different combinations as you find interesting. It's all about the same. Initial mass is the payload plus the empty plus the fuel. Here we're going to have the initial mass 1, payload 1, empty 1, fuel 1. And initial mass 2 is the same thing. Payload 2, empty 2, that's a 1, plus fuel 2. So now the question is how do we link these two equations for the two-stage? If we kind of just think logically through it, if I have a two-stage system, the second stage is the payload on the first stage. Oh, sorry, vice versa. The first stage is the payload on the second stage. Depending on, let's see, how did I do my bookkeeping here? It could be either, depending on how you're defining it. The payload overall, though, is the payload on the second stage. So you have one net payload, which you can define as MP. Payload on the first stage is the second stage, and the overall initial mass is the initial mass of the first stage. So it's just kind of some linking equations of how these pieces fit together. So if you kind of jumble this all around, for the two-stage system, we're going to have gamma is the initial over the payload, same as before. So our initial is initial 1, and our payload is payload 2. And then just kind of put all the pieces in here. So hopefully my writing will be neat enough where you can make out what I'm saying. Initial 1 over payload 1. Payload 1 over payload 2. So I'm just kind of expanding out this equation, which is initial 1 over payload 1, same as it was. And payload 1 is initial 2, so initial 2 over payload 2, which gives us gamma 1, gamma 2. So the composite system initial mass ratio is just the combination of the two parts put together. So that kind of makes it easy to think through what we're going to do for analysis. So as soon as you catch up, is everybody caught up on this part? I'll flip. I need more screens. We'll just write the gamma function the same as it's defined. I'll let everybody finish here. Or maybe I'll squeeze. Let's see here. Gamma 1, as we just did, it is initial 1 over payload 1, which is 1 over 1 minus pi E1 minus pi F1. The same thing as gamma 2 is initial 2 over payload 2, 1 minus pi E2 minus pi F2. So the whole reason we're doing this is not, number one, just to get some equations that make some sense, but now we can start to think about multi-stage systems and start to break it down in terms of things that we know. You know, we've been kind of deriving these equations in terms of these masses up to this point, and so we're going to kind of revert back to that point and start filling these pieces in to make some sense of what's going on. So now if you kind of even think a little bit further, even to do something like the X-43 or the X-51 flights, you know, even to get those seconds of burn time of the engine, they had to resort to a three-stage system. So, you know, it's not even something that's trivial at this point, is getting all the energy you need to get up to that sort of velocity just to test. So thinking of developing a full-scale aircraft, single-stage orbit like NASP, you can think of, wow, that was, somebody was ambitious and some politicians really bit hard on that hook, because that was a big sell. You know, it's a pretty big job to try to accomplish that in one go. So putting these equations here now, that's pretty much it for what I call the notes on this part, because there's not really anything complicated about what we're doing. But I do want to spend some time going through the examples, because I think that that's probably, number one, the most interesting part, but also where if you're having a problem in the homework, that's probably where you're getting stuck. So let's go through two-staged orbit. Two-stage to orbit. We'll do air. Oops, if I can write. All right. So what I'm going to really do is kind of just pull together everything we've done. I'm going to be writing equations in a flurry here and rearranging things. But please stop me and interrupt if I skip over something or I get going too fast here. Orbital energy, our efficiency, our fuel, our thrust terms, and we can rearrange this here. Am I getting this right? One? Yep, okay. Okay, so we'll do a substitution just to get rid of all this nonsense called minus big lambda. So the big piece in the bracket is the minus lambda. Make our lives easy. The gamma function we just derived, we already know is gamma equals gamma 1 times gamma 2. We're just going to expand that same definition we had, 1 minus pi E1 minus pi F1, 1 minus pi E2 minus pi F2. Okay, so now we have a equation. Now you see why we wrote in terms of 1 minus pi F. So we can substitute it into the gamma equation. We have a 1 minus pi F, which will leave us a empty mass fraction on the bottom along with the lambda term. So we put this together. Gamma is e to the minus alpha lambda 1 minus pi E1 and e to the minus 1 minus alpha lambda 2 minus pi E2. So again, nothing complex going on into this derivation, just a lot of substituting terms to get to this two-stage orbit initial mass ratio. So that was what's my question. See, it's like you're a plug here. What's alpha? Yes, it's stage ratio. It's the initial, or it's not the initial. Sorry, it's the energy split for the first stage of the total energy. So actually, well, I guess we'll write on next. So everybody got this part? Maybe I should write smaller. Where alpha is, I guess this will define this, is the energy. Let me see. Where's my notes? Make sure I write the same thing. The energy split or fraction of the total orbital energy provided by the first stage. So if you think of this in terms of staging, you can think of it just alpha as the energy attributed to the first stage, and whatever is left over is energy to the second stage. So if we skip back just for 1 second, you have alpha term and then the 1 minus alpha term. So you can think, if you go through and do this in a bigger sense, which is problem 360 in the book, which I didn't ask you to do, you can start just kind of get this pieces put together. Gamma time equals gamma 1 times gamma 2 times gamma 3, and then you can start to build this out and make some sense of it. It just gets a little bit more complicated. But there's nothing stopping you from doing that as often as you like. So feel free to do that in your free time just for fun. So, which means 1 minus alpha is the energy for the second stage. Okay, so now is where we're going to make some big leaps of faith in order to get something that's going to be easy for us to plot. And that's always the goal, isn't it, to plot something easy. So that's what books like to do, so that's what we'll do. So assumptions. And these aren't in general, these are just to make the nice pretty plots. Two stages. Let's see if I can write this clearly here. The two stages have the same performance. Which means gamma 1, or sorry, lambda 1 is lambda 2 is lambda. So if you kind of refer back to lambda, that was kind of everything that we had there to derive our energy, is the orbital energy, the efficiency, the fuel, and the thrust to drag. So what's the likelihood that that's a good assumption? Well, so I take that back, because the energy part we've already pulled out and put into the alpha term. So it's the efficiency, the fuel, and the thrust to drag. So it's somewhat poor, but you know it's not horrible. But you know, for the purpose of plotting, I guess we'll make do. this is the next one. Oops. The two stages have identical empty mass fractions, which means our empty mass 1 is the same as empty mass 2, which is the same as our empty mass fraction, excuse me, is the same as empty mass 2, which is the same as empty mass. So we can get down to a gamma, which we can boil down to fewer parameters, which is the point here. Oops. Minus 1 minus alpha lambda minus pi e. So this is just for the sake of argument to make this system easy. As soon as you catch up, we'll flip ahead to the picture. So now what you're going to see is eventually I'm going to ask you to play with these things in a way that they're not the same. I'll probably do this in a way where we'll take out the orbital energy term and just leave in the energies, and we'll do things that aren't actually the orbit. We'll play with things. So in that case, you could still think of the energy split being the same sort of derivation. It's still going to be a split of a first stage versus an extra stage. Because everything doesn't have to go to orbit. That's just, it's too limiting. Where are we here? Hydrogen, there we go. So if we look at this guy here, this is, so energy split here is, or sorry, the lambda is the same for both stages. In this case, it's 0.766. And I think if you could kind of dig backwards in the book to one of the other examples, you'll see the numbers that were used to come up with this number. It's kind of following some of the old examples. The empty mass fractions, we already kind of looked at these sort of same representative values, 35, 40, 45%. And so this initial mass ratio, we're kind of talking, and again, loosely stated as a profitable commercial operation, you're looking for gamma less than 10. Well, what you see here is it doesn't exist on this chart anywhere. So even though it's somewhat of a made-up number, you're kind of hitting it right in the middle here. But what you do see when you say the empty mass fractions are the same for both stages and the performances are the same for both stages, you get something that looks like this, which is what? It's symmetric. Yeah, the energy split is giving you the best performance when it's at 50%. So you want each stage to give you half of your total energy requirement. Otherwise, you're going to start pushing something up one of these slopes on this curve where things are getting a little hairy. And so I guess the bad news is if you, for instance, designing something and you're extrapolating and you're wrong on your empty mass fraction, and you're always on the wrong way, right? You always underestimate what your mass is going to be, not over. So if you underestimate your mass, it's going to push you, oopsies, where's my little pen here? It's going to push you this way on this curve. Oops, there we go. It's going to push you this way on this curve where all of a sudden things are getting out of control really quick. So even if you're down to 50% and you're off by on your empty mass fraction, this change here is a net 5% of your total mass for each one of these curve jumps, but you're talking a huge jump in this initial mass ratio. And this is where things start to get out of control. When you try to underestimate mass to sell a program to somebody to get money to do it, this is where things always kind of bite you, as mass. Minimizing mass for anything going into space or into the air is always important. And of course, the other part of this is we're still never going to get to orbit with air-breathing engines altogether anyway. You're not going to have two-stage air and get you to orbit, but either way, it kind of gives you some interesting trends of what's going on here. If we write this now in terms of what that works out to, so we have gamma being symmetric. Gamma is, see if I can write is. Gamma is symmetric about energy split of 50%. Okay. And minimized, I guess. So 50% equal energy split is going to be the best case scenario. So if we look at that, rewrite this equation for gamma min. We just kind of put these terms together. If we know that alpha is going to be 50%, we get e to the minus, wow, hopefully, lambda over 2 minus pi e. It's kind of is that equation rewritten. So for everything being the same, you get 50% energy split, which gives you a minimum initial mass ratio based on, you know, 2 parameters. You kind of got it everything boiled down to just 2 parameters: the empty mass fraction and your lambda, which is all your performance. So everything kind of packages down nice and neat. So it's pretty easy to kind of think through this equation and see what we can do to play with it to get something useful. I guess the note, let's write down notes what I was just actually talking about. Yep.
Is that just what that simplifies down to, or do you expect that whole denominator to be squared?
Oh, yep, it is. Sorry. See? This is why you guys get paid the big bucks. Yeah, it has to be squared. And so if you follow the example in the book, not that it's really relevant now, but it is an interesting exercise, and it takes a little bit more work to get to this point. You can get something essentially for the same thing where everything is the same again for gamma equals 1 over, actually, you don't even need the book. It's the same thing. Lambda over n minus pi e to the n for n stages. You know, that's for everything being equal. So it's not always the greatest argument, but it kind of gets to the same thing. So as you said, the empty mass fraction is a very sensitive parameter. So don't get it wrong, or if you do, you know, be conservative if you're trying to understand things. Bless you. Benefits of staging are much greater for the more marginal systems. Which is larger gamma and pi e. All right, and the same sort of thing in reverse is sensitivity to our energy split is much greater for the more marginal systems as well. Driving them to alpha equals 0.5. So everything is just kind of reading those curves. If we have anything more than a really good empty mass of 35%, these curves are starting to be, you know, not really working to our favor at all. 35% and lower, if we could get lower, things are flattening out where you can kind of pick your energy split maybe more advantageously than where the energy is providing, but maybe something that's more advantageous for your recovery of a first stage or whatever else you might want to try to do. But you know, as soon as your empty mass fraction starts creeping up back on this curve, you know, to these other values of 40 and 45%, the slopes are so hairy. You need to kind of fall into this middle range where things are a little bit flatter, or else you're not going to get anything useful. And of course, if you look at this same curve, what is alpha equals 1? Yeah, single stage orbit. So if you look at alpha equals 1, as soon as you get above this 40% or slightly above 40%, your initial mass ratio is going crazy. But even at this point here, this best guess is you're still around, I don't know, 13 or something. So again, in that whole guise of profitable commercial operation for single stage orbit. So I don't even know if the business case is there, but it's, you know, what this is kind of showing is not even notionally realistic. So fundamental equations are often very insightful. Okay, so we have time for the one last example. So it looks like we will do the whole seminar next time. That's okay too. I hate to cut it in half anyway. So here we go again. Example: 2-stage to orbit, air rocket. So we're going to go through the same sort of issue. We're going to look for R over R naught is about 1. So we can ignore potential energy. Oops. So in that derivation, when we did that derivation, we actually ignored the potential energy early on. You could go ahead and leave that in. You could go ahead and leave the initial velocity in, but it just means things get a little bit more complicated. There's nothing saying that, you know, we have to take it to this extreme. It just makes life easy. So for what we're looking at here, gamma 1, same as before, 1 minus pi E1 minus pi F1, where our fuel mass fraction from our air breathing equations. So hopefully you'll start to see there's a reason I gave you that cheat sheet with all the equations on it, because otherwise it's hairy to start to remember where all this nonsense comes from. Okay, it's not nonsense. Where all these fun equations come from. G naught R naught and our radius term. Okay, so there's the air breathing equation. So this is air, first stage. So we're going to put the fuel mass fraction into there and make some simplification, which gives us gamma 1 is 1 over e to the minus alpha lambda 1 minus pi E1. So same as we did before. We had 2 air breathing stages and it looked exactly like this. So rocket. Again, just going through the same equations that we've already derived. 1 minus pi E2 minus pi F2. And we have a pi F2. So our fuel mass fraction for the rocket, what do we have here? I should write this here. This is gamma 1 here. And this guy here will be our lambda 1, lambda 2, which goes to our gamma 2. I'll let you catch up here. Okay. Can you see that over the monitors? Sorry about that. That was going to be my question to you. Why is there a square root there? If alpha is our energy split attributed to the first stage, and for our air example, if I back up here, we had the alpha and the 1 minus alpha for the second stage. If we're talking energies. So the total energy had to equal 1. How do we get a square root of alpha? Pardon me? No. It's a good thought, though. Look at the fuel mass fraction equations. Remember, alpha is all based on energy. Yeah, the terms aren't in quite the same form. We have a square root G naught R naught for the rocket, and we have the G naught R naught. So it's a difference. The whole term is a different form of energy. So the energy terms are still there, but in the rocket sense, they're reduced down differently. And so in order to count for the energies correctly, now you can go through and just do the math and figure out when it makes sense. But in order to do the energies correctly and make sure you're not over counting for the energy, it ends up with a square root alpha term here. So it's not just a pure, plug and chug. One's alpha, one minus alpha all the time. And you have to kind of think back to the fundamental unit of the difference between the air breathing and the rocket. in terms of how the energy is going to be portrayed. So that's a good question. It's a good thing you're paying attention. But that's kind of a hard one where people kind of lose the focus. But if you think of the G naught R naught term as the energy and the square root of the energy for the rocket, they're not kind of factored the same. So if you put them together, we're still going to do the same thing. So gamma is gamma 1, gamma 2. In this case, we're just going to put this whole mess together. Let's see if I write bigger, it'd be clear. Gamma 2 minus pi E2. So here we didn't, of course, say that the stages had the same performance. So the lambdas are not the same. And the empty mass fractions, of course, are not the same. So everything's a little bit more convoluted here. All right, so let's go to our last picture. Everybody have this guy? I'll go back there in a minute if you're so. Oops, wrong one. There we go. So here's the hydrogen air rocket, two-stage orbit, and of course you see a number of things different, of course, which is you would hope because they're different systems. But this one is obviously skewed to higher alpha. So the first stage requiring more energy. And why do you think that is? Yeah, I mean, if you think of just kind of what the staging part is again, the initial mass of the second stage is the payload for the first stage. So depending on how you're thinking through this system, obviously you don't want to carry that mass as long as possible, but in this case, you actually do want to carry it longer than you would think. That energy split being somewhere greater than 50%. So, so what you see here for the numbers here, and of course this again is made up numbers. Empty mass fraction 1 for the air breather is 40%, and the second stage of the rocket is 20%. So some sort of relative difference, of course. The air breather has got a higher empty mass fraction, almost double, and for the second curve, again, it's almost double. And what you see here is, of course, as the empty mass fractions grow, this curve again is getting to the point where it's way out of bounds. That the slope on this initial line here, you see coming down here for the first stage, is very sensitive. So you have to get somewhere over 40% to even get down to where it's plateauing a little bit. The first part is out of control. You couldn't just take off really quickly and stage. You have to get a lot more energy into the system before you stage. Yeah, yeah. So that's all. I mean, there's obviously way too many options to think about to put on. This is boiled down for one nice little chart. And so the seminar that we'll do next class is talking about single-stage orbit, two-stage orbit, hydrogen, hydrocarbon, air rocket, rocket air, horizontal takeoff, vertical takeoff, horizontal landing. That's why, as I say, it's much kind of take everything we've done in this first chapter and put it into kind of reality. So that's why I think it's a really good summary. And so for this one little case, this is both hydrogen, and you could think if I'm going to pack something inside of something else or tow something with something else, a bigger second stage of hydrogen is probably not the right answer. Hydrocarbon packs down, and what you'll see from the seminar on Tuesday is that's actually the case. Hydrogen first stage, very good. Hydrocarbon second stage, very good.
For these air breathing stages going up to orbit, I'm guessing it's assumed that there's air all the way up there.
Well, no, this is a rocket second stage.
Well, for the other one.
Well, no, and that's kind of what we mentioned before. It's somewhat misleading because you're somehow got enough energy into your system where before you ran out of air, you had enough delta V to get you back out into orbit. So, yeah, it's kind of a big stretch. Where in general, like I said, air breathing engine, depending on what you're going to do and how you're going to quantify it, will stop working functionally around anywhere up to around Mach 15. After that, you need something else. So, yeah, it's somewhat skewed. So anyway, these numbers here, if we just take a few numbers here, whoops. Where's my little pen guy? Where'd that go? There it goes. These numbers here, if I just give you some details, this bottom line here is around, where do we go here? 14.2. So that's the best initial mass. That's gamma. It's 14.2. This guy here on the bottom here is around 9.9. So some pretty interesting ratios, but you know, this one's just starting to break that value of 10. And again, that's just kind of made up. The functions here, lambda 1, lambda 2, again, you kind of have to dig back through the examples to see those numbers. And it's, you know, somewhat based in reality, so I'm not saying they're bad numbers, but of course there's just one specific example, so it's a little bit skewed. The the lambda 2 does come from a rocket with a 400-second ISP, so it's a reasonably good rocket. Maybe not a good upper stage rocket, but it's a reasonably good example for a rocket. Has anybody ever heard of the Sanger vehicle, German vehicle? You kind of follow these circles. It's kind of, I would say, they're equivalent to NASP in the sense that they spend a lot of time and money working on it. So if you're kind of in this field, you always hear a lot about the German Sanger vehicle. And let's get out of here. And so it's a good representative example. So I'll just write a few notes on that. And there's a two-stage orbit, so it's not quite the same, but there's a lot of studies that have gone into the Sanger vehicle. It's been through a lot of, these are little dots. It's a German accent. Sanger, two-stage orbit. There's Germany. Vehicle. And of course, it's a completely paper vehicle, but like I say, it went through a lot of study over a lot of years. It was fairly well understood. Had empty mass 1 of 0.43. and empty mass 2 of 0.23. So, not saying that the numbers on the chart are completely right or wrong. After a lot of years of work, they were able to get something that's somewhat representative, so it's not completely off. For the chart that we just looked at, the minimum gamma is reached as slightly higher than half. Oops. At alpha is about 55%, and the gamma was from about 9.9 minimum to 14.2 based on at least the numbers that were there. So some reasonable range. It was very sensitive, of course, to empty mass. So what you're kind of seeing here of everything we've done, we derived a lot of equations for fuel mass fraction, and sorry, we're a couple minutes over, so we'll wrap it up. A lot of equations on fuel mass fraction, and a lot of the analysis, everything kind of hinges back to the empty mass fraction. Empty, you know, that mass kind of dictates everything else. So we spend a lot of time talking about empty masses relative to fuel masses, and then we get payload as the 1 minus the fuel and the empty. So it kind of gives us all of our performance parameters boiled down to, you know, 3 mass terms, which is a really interesting way to think about it. So you can really start to think now, everything that we're showing here is very sensitive to the empty mass fraction, and rightly so, because that's dictating how much extra junk you're carrying or how little fuel you're carrying for a given initial mass. So what we're going to see in the seminar is really kind of how that boils out. And when you think about these vehicles and project them and extrapolate without having those nice tables of empty mass fraction to build off of, how hard it is to kind of understand something, because there's a lot unknown. Okay? Any more questions before we're done? Please try to have your assignment here beginning class so we don't have ruffling around, and we can get into the seminar. Thank you. Yes. Okay. If we have a what? Really?
Yeah.
Interesting.
It's most likely we'd have to put out an account code anyway, so kind of aluminum. And she said that even if we've done bond coat on nickel or on Inco,
Yeah.
it falls off. And I think it has something to do with the oxidized layer builds up.
That's interesting because where'd Greg go? Oh, he's right there. I'm pretty certain his group at the Navy did this without a problem. But it could be the temperatures you're thinking about as well. We're dealing with some pretty inefficient engines.
But she said that an aluminite coating might just do it.
Oh, interesting. Okay.
So I don't know the temperature,
Greg, did you and Mike and Crowd did the ceramic coatings on the blades? Did you not, or was it just theoretical?
It's actually, so we did it, but it wasn't a coating. The whole turbine itself
Oh,
was made out.
it was okay. That was the difference.
So, having my head silicon nitride, I'm pretty sure. I know that's, most people think silicon carbide, but I think our bearings are silicon nitride and our turbine blades are silicon nitride. Our rotors are moldite, our heat exchanger is moldite.
Okay.
True stabilizer coming out like moldite.
Oh yeah, because what Sybil's saying is, her GE knowledge and folks don't think it'll stick. So, yeah.
When we talk ceramic coating,
Yeah. So we, I think a lot of it had to do with the fact that the scale that we're on. We just
Where's
chose
my-
a machine that crazy.
I'll let it think for a minute.